Hi, in this video we're going to be talking about transistors. In the last video we discussed about the diodes and PN junctions in general. So transistors are two kinds. So we have BJTs, which is bipolar junction transistor, and we have FETs, which is field effect transistor. And then FETs, we have MOSFETs, and then we have JFETs. And we'll study these in the next videos. Today we're going to focus on BJTs. So BJTs, so similar to how we create a diode by bringing the two different kinds of semiconductor together, P and N. So this is how we make a diode. And then we studied before that when you bring these P and N together, there is going to be a depletion region formed here. And we know that in this depletion region, without any external battery, there is a voltage barrier created that's called VB, which does not allow the current to flow through it unless you have an external battery. Now let's talk about transistors. So transistors are three-terminal device as opposed to diode, which was only two terminals. Transistors, we can have two kinds. So we can have a transistor called PNP, which means you have a P-type semiconductor on both sides, and it has N-type semiconductor that is sandwiched between the two. Or you can also have NPN. The important thing to remember is that the middle region here, whether it is N here or P here, has to be very thin and lightly doped. So one side here is called emitter, and one side is called collector, and then this middle portion is called base of a transistor. And always the emitter is heavily doped compared to the collector. So in this case, P has more holes. So in this case, the emitter is going to have more number of holes compared to the collector. The same thing here. So here this is just NPN. You have one side emitter, one side collector, and the emitter side is heavily doped, so it has more electrons compared to collector, and this side is called hole. Now these two, when we look at a transistor in a circuit, they have a symbol that defines what a transistor looks like, similar to just a diode here. So the way transistor is drawn is, so you have a circle, and then you have lines like that, and this. So there are three terminals, 1, 2, 3, 1, 2, 3. Same thing. So you have three lines. The only difference between the way you draw PNP versus NPN is the arrow. So let's say this is my emitter, this side, and this is my collector, and this is my base. It's emitter, collector, and base. So for the PNP, you have an arrow that goes like this, and for the NPN, you have an arrow that goes out. And this arrow is actually the direction of current that is flowing through the transistor. All right, so this is the basics. Now we're going to look at what's happening inside the semiconductor in terms of the holes and the electrons. So I'm going to take an example of the NPN, but the same analogy applies to the PNP as well. So let's take a look inside. So let's say I have NPN. So when I don't have any external battery, what's going to happen is the holes here, the free electrons here and the free holes here are going to try to recombine. So as a result, we're going to have some electrons that move from N side to P side. Therefore, this p side is going to have a negative charge. Now since electrons have gone from here to here, it created holes. So in other words, the holes have moved to the n side, so this is going to create a positive charge here. Same thing on this junction. So electrons are going to move from here to here, so this is going to have a negative charge, and because electrons have moved here, it created empty space, which is a hole, and this becomes positively charged. So these two junctions are going to have a region that we call depletion region. Remember, in the case of diode, there was one depletion region because we had only one junction. Here we have two because we have two junctions. Now, in this region, we will have a potential barrier because we have created this electric field due to the charge. So therefore, once enough electrons and holes have combined, no more electrons or holes can move or cross this junction. So we will have a potential barrier created here, and let's just say potential barrier is VB, and if it is silicon semiconductor, then the value of this potential barrier is approximately 0.7 volts. All right, so far so good. But now I want my current to flow through this whole NPN. Let's say I want the electrons to go here, and I want them to come out on this end. Because remember, the current is just a flow of electrons. So if I want the electrons to go in this direction, obviously, first of all, I need to connect external battery because I need to be able to overcome this potential barrier. So I'm going to just remove this so that I have enough room. So in order for the electrons to move this way, I need to connect this side to the negative terminal of the battery. Why? Because this negative terminal, because of this negative side, the electrons here are going to be repelled. So electrons are going to start moving in this direction. Now what's happening here? So this is a positive charge. Therefore, the electrons that are here are going to get attracted. So electrons are going in this direction. So that's good. We have electrons going this way, and we have electrons going this way. However, we have a potential barrier that we are unable to cross at this point. So therefore, there is no current that is flowing through this whole circuit. So now, let's connect another battery. So I'm going to just remove this so that I have space in this way. So I connect these two, N and P, and I make them forward bias. So forward bias is where P side is connected to the positive and N side is connected to the negative. So this is forward bias. If I do this, now what happens? So now, again, this battery, the negative terminal is going to push the electrons this way. So electrons are going to go here. And here, because this is positive, it's going to attract the electrons. So we now in this case, we will have a flow of electrons from this side. So electrons are going to go like this, and when they come across this junction, some of the electrons are going to combine with the holes, but some are going to go down like that. Because remember, this side, which is called emitter, is heavily doped, so it has a bunch of free electrons. So now we have a current flowing this, we have electrons flowing this way, and we know that the direction of current by convention is the opposite to the flow of electrons. So the current is actually flowing in this direction. So current is flowing this way, I. Okay, so if I label it, then this current here is called IE. This branch here is called IE. Now, So we know that there's a current flowing here. Now what happens on this side though? So on this side, what's happening is when I have mobilized the electrons, because I have now given this external battery which accelerate or excite these electrons. Some of them are going to combine in the base, and then some of them are going to flow down to complete the circuit. But remember, this base is very thin, and this has a lot of free electrons. Even though some have combined and some are going this way, some are going to leak. They're going to cross this base and are going to enter the collector this side. And once they are here, and this is also now connected to the positive side, so electrons are going to get attracted. So there is going to be a current that is flowing in this circuit as well. And this current, this is the collector. So this current is called IC. And this current that is flowing out of the emitter is called IE. And this current that is flowing down here is through the base is called IB. Now it might not be clear from this diagram, but IE is equal to IB plus IC always. No matter whether it's PNP or NPN, this always holds true. And also another thing to remember is that this IB is the reason why we have IC flowing. So if I had not completed this circuit, I would not have anything on the IC. So just remember this. And now let's move on to further analysis. Okay, so this is a circuit, just one example, but you can connect, you can have different configurations of how the transistor is in the circuit. So we have 3 different modes of configuration. I'm going to look at what those are for transistors. So first one is called common emitter. What does that mean? So I'm going to take an example of still NPN transistor. So what does common emitter looks like? Let me draw a transistor a little differently. I'm just going to rotate it a little bit. So like that. So my emitter is here, collector is there, and base is there. And if I have my input, connect this to battery, that, and I do that. Oops. And then I have a resistor here. Let me call this VCC, let me call this VBB, and this is my input. Alright, so this is my NPN transistor, but this configuration is called common emitter. Why is it called common emitter? Because I have this emitter which is common to this output circuit and the input circuit. By the way, this is called load resistor. So think of it as a point where you are where you're measuring the output. So, and I'm measuring the output here, V out, let's just say, or even I out. And then this is my input circuit. So for transistor to even work, this input circuit has to be forward bias. Okay, so this is called common emitter because this emitter is common between the output circuit and the input circuit. Now the next one is called common base. So common base, as you might have thought, so common base is going to have the base is going to be common between the output and the input circuit. So let's draw it. So I have my transistor now this way, and then I have my, actually before we go there, let's label the currents. So we know the current that comes out of the emitter is called IE, and the one that goes into the base is called IB, and the one that comes out of the collector is called IC. And we can verify that IE has to equal IC plus IB, and that makes sense. Now this arrow should be going into the collector, so the current is going into the collector. Okay, so here and that makes sense, right? So IE comes out, and then at this node it becomes IC and IB, and it matches the directions of the batteries. So I think it looks good. All right, so now this one, so here let me complete the circuit. So I have let me just draw my input. Let's say this is my VIN, and I have battery DC volt here, and then I have my load resistor similar to how I had there. So this is just where I'm measuring my output, and I have this. So again, this is the BCC and this is VBB, and in this case this is also NPN. My emitter is right here, so this is my emitter. So now in this case, again, this is the emitter. So remember, the arrow tells us the direction of the current. So IE flows this way, like that, and then IB flows this way, and IC flows this way. We are measuring the output this way. So if you want to analyze, let me just erase this from here so that I can use the same page and try to analyze what are we getting out of these circuits. Okay, all right, so now let's analyze the common emitter. So this is my common emitter circuit, but let's measure the current. So because we do know that IE is equal to IB plus IC, as we saw before. Now what is my output current? So my output current is IC, because that's what's flowing into my load resistor. And what is my input current? My input current is IB, because that's flowing through the input supply. So this is just output over input in terms of the current, and there is a term that defines it, and it's called beta. And a lot of times this beta will be given to us, like when we look at the data sheet for a transistor, it will tell you what is the value of the beta. And this is very, very important relationship, because as we have seen before, that IC is only possible when you have some IB. So IC is equal to beta times IB. So that's one relation we need to remember. So this is 1 and this is 2. And then let's look at the common base. So if you look at the common base and try to do the same analysis. So for the common base, my output current is IC, because that's what's flowing through this RL. So this is IC. And my input current, which is flowing through my input, is IE. And this term is also defined by alpha. So now this IC over IB is going to be less than 1. Why? Because we know that IC is less than IE, therefore this alpha is less than 1. So what does that tell us? That tells us that this common base configuration, here the output current is actually less than the input current. So in the analysis that we'll do further, we will mostly use this common emitter configuration because that is most commonly used. Now, another thing that we want to remember from here is the relationship between the beta and the alpha, because we have this equation up here, so it's easy to derive what is alpha and beta, like how are they related. So if I start with alpha equals IC over IE, and I know that IE is equal to IB plus IC, so if I do the math, what I'm going to get is alpha is equal to beta over beta plus 1. So I think this is enough for us to know in terms of the relationships. Next, we want to understand the modes of operation. So this is just how they are configured. But next we want to understand the modes of operation for various transistors. So as we saw in the case of the diode, we only have two modes of operation. One was it can be either on or it can be off. Meaning when you have forward bias, it's on. When you have reverse bias, it is off. But in the case of transistor, we actually have three modes of operation. So let's take a look at what those are. Alright, so the first mode of operation is simply called cutoff. So this cutoff mode is when the transistor is off. And this happens when the input circuit, so if I draw my my common emitter one again, so let's just draw it again. I should not have erased it, but now I have to redraw. So this is my common emitter circuit. Okay, so this is IE again, and then this is IC, and this is IB going this way. And all of these circuits are grounded, but we just don't draw that for simplicity, but all the circuits are, they have a ground. Okay, so this is my common emitter. So now remember, when we were doing the analysis at the electron level, we said there is a potential barrier of 0.7 volt, especially for the silicon-based semiconductors at the junction. So therefore, for the current to flow from this side to this side for this input circuit, it has to be forward bias. And more importantly, because of the junction, we know that there is going to be a potential drop of 0.7 volts at this junction. So that means the voltage here, let's call it VB, and let's call the voltage at this VE. So that means VB has to be greater than VE by at least 0.7 volts. So when that's not the case, then we have a cutoff. So that means in the cutoff region, during the cutoff mode is when there is no current flowing. So this IB is 0, and so is IC, and so is IE. So IB is 0, IC is 0, and IE is 0. Then second mode is called saturation. Now saturation is the opposite end. Saturation is that the current that can flow in the circuit, especially this IC, has maximized. So even though you keep increasing IB, there's going to be a point when IC no longer increases. Remember this equation that we derived, that IC is equal to beta times IB. It means if you increase IB, then you're going to also increase IC proportional with this proportionality. Now, so why does this saturation happen? So if we take a look at a circuit, let's say I have a circuit where I have my transistor like that. This is my emitter, and this is my base, this is my collector, and I have this connected to the 10-volt battery, and then I want to measure my VC here. So this is the base, and we know that the base current flows like that, IB and IE. So this is IB, this is IE, and then collector current also flows downwards into the collector, so this is IC. Now if I increase this IB, then I know that IC is going to increase. When IC increases, then there's going to be a current that flows through this resistor, and there's going to be a potential drop, and the potential drop that is going to happen here is IC times R. So therefore this VC is going to be equal to 10 minus whatever the potential drop here is, which is IC times R. So now if I keep increasing IB, then I'm going to have more IC, which means this drop is going to be going up. But at some point, if you keep increasing IB, there's going to be a point where the drop demand for this drop is going to be more than the supply voltage, which is not possible. So that's why when that happens, you're going to have saturation, which means IC no longer increases. It becomes like a flat line. In reality, you don't have to wait when this becomes 0, like VC becomes 0. So at saturation, the value of the VC is somewhere equal to 0.3 or 0.4 volts. Okay, so let me just erase this and kind of write fact here that VC at saturation is somewhere equal to 0.3 or 0.4 volts. Let's just keep it 0.3. Okay, and then also here I want to say one more thing, that here in this specific case, when you have a cutoff, then VB is less than VE. Now, if I were to draw the output input characteristics for the transistor, so specifically if I want to know what is my IC when I have different values of IB, then let's just say this is volts and this is current. This volts is the one between the VCE, this one. So if let's say I have fixed my IB and I try to measure the value of IC, so it's going to like go like this and then become flat. So this is at some value of IB. Let's just say this is 20 microamps. At this value there's going to be some amount of IC. Same thing, so let's say I increase my IB and then I try to do the same measurements. So here this IB is 40 milliamps. So if I keep doing that, what I learned from here is that at the IC saturates at some point. So this is what happens at saturation. Now in between these two modes, where you have a cutoff and where you have the saturation, is a linear relationship between the IB and IC, and that region is called active mode or active region. The transistor has 3 modes of operation, and we see cutoff, we see saturation, and we see active. And during this active mode is when the current is flowing through the transistor, and specifically for the NPN in this mode, VB in this mode, VC has to be bigger than VB, and this has to be bigger than VE. So just remember that this has to be true when it's in the active mode. Alright, so I think that is all about transistors, the basics at least. Now we can try to do some problems, circuit problems. So let's do that. Okay, let's take an example of this circuit. So I have a resistor, and then I have a common emitter transistor, another resistor, and then I have a ground, and I have here, and then I have 10 volts, and this resistor is called, it is 4.7 kilo ohms, and this is my VC, this is my VE, and this is my IB, and this again is connected to the power supply, 4 volts. This is 3.3 kilo ohms, and I know the emitter current flows out of the emitter, so this is IE, and I know the collector current flows through into the collector, so this is IC. The question here is, I want to know what is VC. Or actually all of these, I want to calculate VC, VE, IE, IB, and IC. So we can analyze the circuit as is, but if this does not look familiar, then we can actually redraw this circuit in terms of the circuits that we have seen before when we were doing the different configurations of the transistors. So if we were to redraw, it will look like this. You have a transistor, that, and then you have a supply, that. Okay, so this is my 10 volts, and this is 4.7 kilo ohms, and this is IC, and this is the collector, and this is where I'm trying to measure my VC, this is where I'm going to measure my VE, and I have a current IB flowing this way, and I have IE flowing this way. I actually forgot to connect a resistor here, this one. So there's a resistor here, 3.3 kilo ohms. Okay, so now I want to analyze this circuit. So from what we have learned previously, we know that there is going to be a voltage drop here of 0.7 volts. So therefore, if I analyze just this circuit, and this is 4 by the way, so if I analyze just this circuit, I know that VE is 4, which is the voltage at this point, minus 0.7 volts. So VE we know is 3.3 volts. Good. Next we know VE, and we know that this is a resistor, and here this is all connected to the ground. So therefore VE, if we want to calculate IE, that is easy because we know Ohm's law, V equals IR. So IE will be equal to whatever the voltage drop here is at this resistor, which is VE minus 0 divided by 3.3 K. So 3.3 volts divided by 3.3 K, which is going to give us about 1 milliamps. Okay, so now we know these two things. Next, we want to find IC, VC, and IB. So if we talk about VC, actually let's try to find the current first. So IC. So from the previous relations that we have seen, we know that IC equals beta times IB, but we don't know IB yet. So let's see what else we know. So we know that alpha equals IC over IE, and we do know IE, but we don't know alpha. However, we can calculate alpha from the beta, and I forgot to give you the beta. So beta is usually given to us, and in this case the beta is, let's say, 100. So therefore I can calculate alpha, which is beta over plus 1, so 100 over 101, and we know that IC is related to IE by this relation. So IC is equal to alpha times IE, which is that, and then 1 milliamps. So if we do the calculations, we are going to get 0.99 milliamps. Okay, so I think the rest of the things are easy. So if we look at the VC, the VC is equal to going to be 10 minus the voltage drop here. So 10 minus IC times R, which is 10 minus IC is 0.99 milliamps minus 4.7 kilo ohm resistor. So if we do this calculation, we should get 5.3 volts. And finally, IB is easy because We know that it's just equal to IE minus IC, and we know IE and we know IC. Okay, so this is all good, but remember that these relationships, alpha and beta specifically, is only valid when you are in the active region. Therefore, while we were solving this, we assumed that we were operating in the active mode. So now it's important to make sure that we check that our assumption was correct. So how do we check our assumption? So if you go back here, we said when you're in the active mode, your VC has to be greater than VB and this has to be greater than VE. Let's see if that's the case. So VC is this, and VB is 4, and VE is 3.3. So our assumption was correct because VC is greater than VB is greater than VE. So good. So in this case, the assumption was correct, so our calculation is correct. However, this may not always be the case. So there could be a case, so for example, like if I change this 4 volts to 6 volts and try to do the same calculations, you might end up in a situation where you have calculated your VC, VE, VB and all of these currents, but when you go back and try to check your assumptions, you might see that your assumption was wrong. So in that case, you will need to find out whether you're in the cutoff mode or you're in the saturation mode, and it's actually pretty easy. Cutoff mode is very easy. So whenever the input circuit is reverse bias, you're going to be in the cutoff mode. So if you're not in the cutoff mode and not in the active, then you know you are in the saturation. I think we'll stop here. Next, we're going to talk about MOSFETs in the next lecture. So I'll see you in the next one. Thank you.